So we're going to continue our next lesson in this unit. So far, we've talked about momentum and impulse, conservation of momentum. And then just the previous lesson, we introduced the concept of work and power. So today, we're going to kind of complete the concept here by talking about energy. So let's look at our objectives. So the first is to define the relationship between work and energy. This is really central to the lesson here today. And then we're going to look at two types of energy, potential energy and kinetic energy, and determine how do we define and calculate each of those types of energy. So let's define energy in the broadest sense from a physics standpoint. It's the property of an object or a system that enables it to do work. Now notice the unit of measure for energy is the joule, the same unit of measure that we used for work. Remember, work we defined as applying some force to move an object a certain distance, right? To work against another force and move that object or cause it to accelerate. So let's look at some types of energy, right? We've got light energy, we've got energy in waves, could be very powerful. We've got geothermal energy. We actually have that pretty close to us here in Santa Rosa, up in the geysers. Solar panels, solar energy is becoming a larger and larger component of our energy generation, including wind power as well. And some of you, this may be what you think of when you think of energy. Your favorite energy drink. I actually don't recommend you drink this stuff. It's not the most healthy, but it does get you going. So the specific type of energy that we'll be working with is mechanical energy. So there are other types, right? The chemical energy, electrical energy, wind energy, et cetera. But we're going to look at the specific category of mechanical energy. And the first thing we're going to do is look at a couple examples and see if we can apply this definition of energy as a result of either doing work to a system, or if you have energy, that system can now perform work. So let's look at an example here. Here is a watch mechanism. Now, this is kind of the old-fashioned watch versus an electronic one, but it had a mechanism, mechanical mechanism, that causes the hands to turn. Now, what did you have to do in the old days with watches? We had to wind them up. So the object in the system that acquires the energy would be the watch spring, right? We have to do work to twist that spring and wind it up tightly. And now that the spring has energy, what work is it able to do? Well, we can see right in the video, right, that the work that the spring does is to use its energy to move the hands of the clock. Okay, so there's an example of this concept of work and energy and what their relationship is. Let's look at another example here. Let's watch this archer. Now that's a pretty fancy bow that she has there. She is a competitive archer. The bow is actually called a compound reflex. It has a series of pulleys on it that when you first pull it back, it's really stiff, but the further you go, it actually requires less force to hold it. So it's really easy to hold it very steady until she has it aimed and ready for the arrow. So the same question, if you look at that system of the bow and arrow, which part of it has acquired the energy? And the answer is the bow and the string, right? As she pulls back, she's doing work to stretch out that string, to stretch out the arms or bend the arms of the bow. Now that arrow has the ability to do work. What's the work that it's doing? It's causing the arrow to move, to accelerate. Let's look at one more example.
We're the legendary shots, and this is a catapult shot. Oh! Oh! Oh my God!
From a different view here.
Another ride.
Yeah!
Okay. I'm not sure how many times it took them before they were able to master that. But let's go back at the beginning here and look at the catapult. So it's hard to see here a little bit, but the far end of the catapult, not the end where the basketball is attached to, has some big rubber straps, or basically big rubber bands or bungee cords. Okay, so as he pulls that arm down, what is he doing? He's creating energy in that spring and those rubber bands of the catapult. Now that catapult has the ability to do work. And what's the work? Let's watch it one
The
more time.
legendary shots, and this is the catapult shot. Oh!
So the work that the catapult is then able to do is cause the basketball to set into motion, to accelerate the basketball. Okay, so that's this concept of energy. Energy, by definition, is an object or a system's ability to do work. So when work is done to an object, we increase its energy. Okay, so as we wind up the spring, or we pull back the bow and arrow, or we stretch the catapult spring, we're doing work to the object and we're increasing that object or that system's energy level. When the object performs work, right? When the watch spring unwinds and turns to hands, when the bow is released or the arrow goes flying, and when the catapult's released and the basketball flies, right? The energy in the system is now decreased, because it's doing work to the object, right? To the watch hands, to the arrow, to the basketball. So this leads us to this first important concept of the work energy theorem. And it basically says this: the work is equal to the change in energy. Okay, so work equals change in energy. So the amount of work we do to an object is how much it increases its energy by. Or if the object or system performs work, that's how much its energy is going to decrease by. Okay, so these are equivalent. We call this the work energy theorem, okay, or the work and change in energy equivalency. And remember, when we defined work and energy, we found that they have the same unit of measure. They both have joules, and this is why work and energy are basically interchangeable. The two forms that we're going to look at are potential energy and kinetic energy. So let's define potential energy first. Typically, if we're talking mechanical potential energy, it's the energy of position related to the relative position of two objects. So for example, the surface of the earth and a ball, right? How far above the surface of the earth is the ball? Has it been raised? Okay. The symbol we use for potential energy is capital P, capital E. And again, notice no matter what type of energy, it will always have the same unit of joules. So let's look at an example. We have a ball that has a weight of 100 newtons, right? So it would be a mass of 10 kilograms, but if we multiplied that by the acceleration due to gravity, right, we would have a weight of 100 newtons. So gravity is pulling down on that ball with a force of 100 newtons. Now, when that ball is sitting on the ground, on the surface of the earth, we're going to call that our zero energy reference point. Okay, well, so we say the object or potential energy of the object has zero potential energy when it's resting on the ground. Now, that's somewhat arbitrary, but we do need to define a reference system with potential energy and define the point at which it has zero. And we're going to, for almost all the problems we work on here, it'll be when it's on the ground, on the surface of the earth. Now, what happens if we raise up this ball 2 meters? Okay, so obviously it takes work to lift that ball. We're going to do work that's equal to the force, 100 newtons, right, against gravity, times the distance that we moved it, 2 meters. Okay, so the potential energy of the ball is now equal to the amount of work it took for us to lift it up. So let's do the math, right? We just said the force is 100 newtons to lift up, basically equal to its weight times the 2 meters. So we did 200 joules worth of work to raise that ball. Now, how much did its energy change? We increased its potential energy by 200 joules, right? So we did work to lift it up, and now that ball has 200 joules worth of potential energy. Now, how could we release that energy? Well, letting it basically fall back to the ground. And as it's falling, right, it's going to gain speed, and it will have the ability to do work, release that energy. Now, if we get really specific, right, about gravitational potential energy, we can adjust our formula a little bit more for potential energy. Remember, we said it was basically the force times the height. But remember, the force, if we're lifting an object against gravity, is basically its weight. So it's mass times gravity. So that's where the mg part comes in. And then h is for the height. So for a lot of the problems that we'll do, we're going to calculate the gravitational potential energy by mgh, mass times the acceleration due to gravity times the height. So we're going to call the surface of the Earth a zero height, so therefore it would have zero potential energy at that location. So let's see if we can apply this to our example again, right? This time I'm giving you the mass of the ball and stating that it has zero kinetic or potential energy when it sits on the surface, on the ground. Now we're going to lift it up again, those 2 meters. So the change of potential energy is going to be mgh. It's mass of 10, the acceleration due to gravity of 10, and the height of 2. So we multiply that together, we get the same result we had on the previous page, right? 200 joules is the amount in which we increased its potential energy. Now, since it started at 0, we increased it by 200, but that is the total potential energy that it has at this point, 200 joules. Now, what happens if we were to take this ball and roll it or slide it up a ramp? And the ramp, let's assume, is frictionless, right? It's going to roll up without any force required to overcome the rolling resistance or rolling friction. So let's do that. Let's slide it up the ramp. And what if we say that ramp was 4 meters long? So how much work did we do to it? Well, remember, the work that we did to it is only equal to the amount that its potential energy changed. So even though we rolled it up a ramp, it turns out it has the same potential energy as if we lifted it straight up, right? Because it's going to be 10 kilograms times 10 times 2, we'll still have 200 joules. Okay. Now, it's a little easier to push it up a ramp, right, than to push it, lift it straight up at times, right? A ramp could be a useful tool for us, or a machine in essence, but the total change in potential energy is the same. So the path that it takes really is not important when we calculate its change in potential energy. All we care about is how much further above the surface of the Earth is the object when everything is said and done. So it's just that vertical distance, that vertical direction that we care about. All right, last topic here, kinetic energy. Kinetic energy is the energy of motion. So the formula for this is a little more complex, and we're not going to try and derive it here in this lesson. I'm just going to give it to you. And it's 1/2 times the mass of the object that's in motion times the square of the speed. Okay? So it's just the speed or the velocity that is being squared here. Okay, so 1/2 mv squared is the formula for kinetic energy. Notice the symbol is capital K and then large E for kinetic energy, and the units again are joules. So a moving object has the capability or the ability to do work. So let's look at an example. Let's say we have this car that's in motion. It has a mass of 1,000 kilograms, and it has a velocity of 20 meters per second. And my question to you is, what is the kinetic energy of that car? Well, it's going to be pretty large, right? These are big numbers to begin with, and then we're going to square the velocity. So let's plug it in, 1/2 times 1,000 times 20 squared. Now, the only thing to be careful of is when you're calculating kinetic energy is make sure you square the velocity first, then multiply it by the mass, and then divide by 2. So if we go ahead and do that, we see that this moving car would have 200,000 joules of kinetic energy. So the kinetic energy of a moving object is equal to the work required either to bring it up to that speed or to bring it to rest, right? Remember the work energy theorem. The amount of change in the energy is equal to the amount of work done on the system. So in that previous example, if we had to increase the energy by 200,000 joules, the engine would have to do 200,000 joules worth of work to get it up to that speed. Likewise, if we bring it to a stop, the braking system, right, is going to have to do 200,000 joules worth of work to bring it to rest. So we can actually say that, yes, we calculate kinetic energy as 1/2 mv squared, but we can also replace kinetic energy, or the change in kinetic energy, with our formula for work, force times distance equals 1/2 mv squared. So how does the kinetic energy change if we double the speed? Let's just play around with these formulas a little bit here. And the answer is that it would be quadruple. Remember, we're squaring the velocity. So if we double the speed or velocity, we quadruple the amount of energy. And therefore, if we quadruple the amount of energy, it also takes 4 times as much work to either speed the car up or to slow it down. So let's look at some examples. Let's say we have a car that's going 30 kilometers per hour, and we hit the brakes and push them as hard as we can, and it takes 10 meters to bring it to a stop, right? We skid or lock up the wheels and it slides for 10 meters, okay? Now, what happens if we double the speed? How does that affect the energy? Well, it's going to quadruple the energy. And so if the energy is quadrupled, then the work done also has to be 4 times as much to slow the car down. Now, the brakes can only apply so much force. That's going to be the same. So what does change? The distance that we skid, right? So the distance is now going to be 4 times, or 40 meters, to come to a stop. Let's do it one more time. What if we're traveling at 120 kilometers per hour? How much distance will it take for the brakes to bring the car to a halt? Well, we're going to double the velocity again, so we're going to quadruple the energy again, which means 4 times the distance to do the work and bring it to a stop. So here's a key example of applying physics to our everyday life, right? When you're in a moving car, and most of you are drivers or soon will be, it takes much more energy, 4 times as much energy, and 4 times the distance to stop the car as you double the speed. Okay, so remember that, right? If you're driving at 30 miles an hour down the street and then you go to 60 miles an hour, that's going to take 4 times the distance for you to stop. So think about that in terms of how close, right, you follow other cars on the street. All right, one final example here, and then we'll wrap this up. So there's a hockey puck sliding across the ice. It has a mass of 0.1 kilograms. And the player exerts a constant 5 Newton force over a distance of 1 meter. He's going to hit it with his hockey stick. So 2 questions. How much work did the player do to the stick? And what is the change in the puck's energy? So the work, we know that, right? Force times distance. And we're given, what are we given? The mass, the force, and the distance. So we have everything we need to calculate the work. So if we plug in 5 newtons times 1 meter, we get 5 Newton meters, or 5 joules worth of work. Now, assuming the hockey puck was at rest, right, before he hit it, how much did we increase its kinetic energy, right? We now have set it into motion. Well, the work energy theorem says that the amount of work is the same as the change in the energy. So if we did 5 joules worth of work, the kinetic energy also increased by 5 joules. All right, so that's it. We've learned to define the relationship between work and energy with the work energy theorem, and we know how to define and calculate the 2 types of mechanical energy that we'll be working with in this unit: potential energy due to gravitational forces, right? How far have we lifted it? And kinetic energy, the energy of motion.